right, thanks. The charm. So our third speaker is Sayantan, who's going to tell us about distribution learning, meeting, graph structure sampling.
Yeah. Okay. First of all, am I audible? Yeah. Okay. First of all, thank you very much for inviting me. I mean, it's an amazing place to be. I'm very happy. The experience has been very good. Okay. So I'll talk about distribution learning meets graph structure sampling. This is a joint work with Arnab, Sutanu, Phillips, and Vinod Chandran. Although the title doesn't say it explicitly, as we go throughout our talk, we'll see the connection between two different computational models and how their interplay gives us new distribution learning algorithms in specific classes. Okay, so roughly this will be our plan of today's talk. So let's jump onto it. So as everybody know, I'm not going to spend much time here. So here just we are assuming that this unknown distribution P star, we are getting IID samples from it, and we want to output a distribution P hat, which is close to P star with high probability. Okay, and in some cases, instead of presenting a particular single distribution, you can also give it as a like a sampler kind of thing, and you can make assumptions on P star, you can make assumption on P hat, and that changes these complexities. Okay, so this is our central problem that we'll be looking into. And throughout this talk, we'll be only considering KL divergence. And there's a particular reason for it, and we'll go over there. Okay, but throughout this talk, we'll be only considering KL divergence. Okay. So as you already know, like there are two components to it. So how many samples we need from P star, or as well as like how long does it take to get this distribution P hat. And both are important to us in this context. And there are some trade-offs that is also there. Okay, so like for motivation, like I think I should not give motivation here, but like any class, I mean, in clustering problems, you can also think like a distribution testing problem, because if you learn this distribution in a sense, it also gives the marginals of these colors. So, and there are lots of other things like Yash will talk about tomorrow, like this distribution testing uses link verification. So it's all over the place. So primarily in this talk, we'll be considering among high dimensional distributions, say, but we'll be only focusing on discrete distributions. And suppose our input symbol is from K and we have n dimensional distribution. So in general, learning such distribution takes exponential sample and time, and this is a folklore result. But unfortunately, like high dimensional distributions are quite prevalent. So can we do something about it? So arbitrary distributions, we are kind of not super hopeful, but can we at least learn some importance of classes? And it turns out that we can. Okay, so one of the primary thing that we'll be considering in this talk is the Bayesian networks. So a Bayesian network is something like this. So you have a node and it has its like parents, and once you fix the values of these parents, like the say B and E, the value of A is determined independent of the other nodes. And by Bayes rule, it also factorizes. And a Bayes-net distribution is basically a distribution that is defined on a Bayesian network. Okay. Yeah. Okay, so suppose we have a graph like this, which is a directed graphical model. So suppose we have these three nodes, say B, E, and A. So once you fix the values of B and E, it automatically determines the value of A, like the dependency. But once you fix, so it has two in degree 2 here. So other than those B and E, like it is independent of the rest of the nodes. And it basically factorizes into different parts. And this actually helps in the sense that representing this takes n times k to the power d plus 1 space instead of like k to the power n space in general. So at least space-wise, even we are better. And yeah. So like one common notion of complexity in Bayesian networks is this like what is the in degree? So here in degree is d. Throughout this talk we'll be assuming d is some small constant, and it turns out that you can define any distributions on n nodes with a Bayesian network of degree at most n minus 1, because potentially a node can only depend on all other nodes, but then like the dependency is n, so we are not happy, so we'll be considering only bounded in degree. Okay, so before I jump into it, so I'll define some variants of distribution learning here. So first is this realizable learning. So had this distribution P star that from where we are obtaining samples belongs to a particular class C of our interest, say monotone distributions or k-modal distribution or something. Similarly, it may be arbitrary distribution P star. Similarly, on the other side, so these were the input side. On the output side, we can consider proper learning in a sense like we want to output a distribution P hat which belongs to this particular, say, class monotone distributions. Or improper learning, we can output a mixture of this class distributions. So this is some sort of a very broad picture. So like this is the all possible distribution, and there is a particular concept class, say monotone distributions. So if your P star, the input distribution is in the class, that is realizable. And if P hat is also in the class, it is proper. But if they're outside, like P star is outside, it's agnostic. So it's arbitrary, it doesn't matter from where it is coming. Or like P hat, like it is outside the class. Okay. So these are the four like types, and these two types are input, two types are output. So I'll briefly summarize our results in 2 slides. I'll explain them later, but like just to give a gist. So we consider a particular class of Bayesian networks called pre-structured distributions, and we design new algorithms for it, which has this sample complexity, and it improves like the previous known bound. Like previously the dependence was k cube, which is now k square, and it is kind of a folklore that in this setting there is a famous algorithm some of you may know, like this Chow-Liu algorithm. To the best of our knowledge, this is the first algorithm that doesn't follow that route, so this is a new approach. So this is for tree structured distributions. So tree structured distributions are Bayesian networks where every node has in degree 1. But we can consider much richer classes of distributions, say chordal distributions. So chordal distributions, I'll show it later, but like in a gist, like chordal distributions are defined on chordal graphs. And in that case, we can learn this with this number of samples in polynomial time. And this actually generalizes these tree structured distributions or a slightly general notion of poly-structured distributions. And previously nothing was known for chordal distributions. And this is quite useful in causality sense. Okay, so these are our 2 spotlight results. Any questions?
That you provided?
No, they're not matching. They're far from matching. That's the open question. Okay, so now I'll go to, so this is the first model was this distribution learning model. You are getting IID samples, you want to learn it. Now we'll consider a slightly different computational model called online learning model. This is from like reinforcement learning literature. So suppose like, so there is a game between environment and the player. So the player like predicts some xt, and then player predicts ft hat, and then environment comes up with xt, and it suffers a loss, like how far is it in its prediction, and this play goes on for say t rounds, and the goal is to minimize the total loss that it is incurring. Okay, so this x1 to xt, for example, here will be samples, like this can be technically arbitrary in normal online learning setting. And there is also another model called online learning with expert advice. So for example, like without saying this, so let's assume that like we're making a portfolio and like it's a stock market. So we are listening to lots of experts' opinion, and at the end of the so at every day we see the experts' opinion, and based upon those opinion, we are making some money, like choosing some stocks, and at the end of the day we are seeing like which one is better and how much we are losing. And the goal is to see that in hindsight how far we are from the best expert. So at every round we cannot change like we can change experts, but when we are comparing, in hindsight we are comparing with the expert that is best. Okay, so this is called regret in this literature. This bound is known as regret, and the goal is to minimize the regret of this algorithm. Okay. So for the context of distribution learning, these samples, these XTs will be some samples from this unknown distribution P star, which will be IID samples, not like arbitrary samples. And here our expert will be all possible candidate distributions. And we want to design algorithms such that the regret minimizes. And somehow like these two things are connecting. So that comes in the next slide. So any questions on the model? Okay, cool. Okay, so before I jump, like there is also this notion like this is the regret and we want to minimize the regret. And here we want to have, so the game goes on for capital T rounds, and we want to design like the entity of interest here is the average regret, and we want to have it a little of one, and that is called no regret learning. And it is very like well studied in the literature. Okay, so this is the slide that is the most crucial part of our this talk. So it basically says that if you are getting samples from a distribution P star and you are outputting predicting a distribution P hat at round T, it is bounded by the regret of this algorithm plus the minimal distance. Like you cannot beat minimal distance, but you are not making too much error on this regret. So if you can somehow minimize the regret, then it gives you a good learning algorithm in KL. Oh, so A is the like your online learning algorithm, and C is the like the expert classes. Yeah, at each round. So you'll be running it for T rounds. At every round, we have to like predict a distribution PT hat, and in total, it turns out that the KL divergence between P star and PT hat is upper bounded by this quantity on the right hand side. And the second term on the right hand side, we cannot beat it because it's the minimum, but we don't want to do much worse than that. So our goal here is to minimize the second term on this equation, the regret. Okay. So it basically says that if we can design good online learning algorithms, we can learn distributions well in KL divergence. Okay. And the proof is not too large, so I'll be putting it here. How much time is that? Okay, then I'll be good. Okay, so before that, like if we run this enough, like so at every round you're seeing these samples, and once you gather more and more samples, you have some better understanding of the distribution. So in a sense, the more the round it plays, the better your guarantee is, in a sense. But we'll be happy with epsilon, and epsilon depends like this. And eventually, like these are expectations, so we'll apply some concentration bounds to get with high like PAC type guarantee. This is our proof. So this is just, so I'll just give a very single slide proof, although it's a big, but like it's kind of cute. So I thought of keeping it here. So basically, okay, so let's go there. So this is the thing that we want to prove. Okay, so let's start with the average notion of average regret. So we have regret and we are averaging it over T rounds, and we are just rewriting it with adding this term P star XT. And then it boils down to, like, if you do linearity of expectation and conditional expectation, if you take this expectation on this t rounds, it basically cancel out this, and then there are some Jensens, and then comes down to this. So not too much technical proof, I would say, but it's a bit math heavy in symbols, but I think this is very cute. This is my personal biased opinion, of course, but yeah. Okay, so we have this result, and learning this thing basically boils down to designing better regret algorithms. So now I'll go over briefly over the total details, and then I'll go over switch to like our techniques if I have time. So for improper real-life, so these blue things are our new results, and so there is some lower bound. So all these learning results are in KL, so they're not in TV. Okay, so these blue results are our results, and this black, so these were previously known. But the problem is here, although we are considering Bayesian networks of in degree D, even then these algorithms, although they are like polynomial in n samples, they do not run in polynomial time, not in poly n. So we want something even better, like best of both worlds, like we have good sample complexity as well as good time complexity. But it turns out that, like, at least for general Bayes nets, we do not know anything. But for special classes, we do know anything. So this is a tree structure distribution. So tree structure distribution is basically a Bayesian network within degree 1, and it factorizes very well. And for this setting, we have algorithms that runs in poly n time. And here I would like to mention that also what we have said, like this dependency on nk square, it was previously known to be k cube, the dependence on the alphabet size. So in this work, we got it k square, and it was also already known to be tight. So we matches that bound in alphabet. And this also runs in polytime. Yeah, the author is here, I think. Yeah, okay. Okay, so this is for tree structure distributions. So what about like chordal structure distributions? Okay, so chordal structure distribution is, so you take a graph G which is undirected and chordal graph, and you want to define a DAG on it, and it turns out that there can be cycles. So the very first thing, that is a tree structure distribution, every node has in degree 1, at most 1, like root. But the middle picture, it can, this node 1 has in degree 2. So this is, although the undirected graph is a tree, the in degree is not 1, so it is not exactly tree, it's called polytree. And we have finally the chordal structure distributions, which skeleton is not a tree. There can be cycles. So this is our thing that we'll be working on. And this actually generalizes both tree as well as polytree distributions. So if we give a design a better algorithm for chordal distribution, this gives algorithms for others. So previously, before our work, like till polytree structured, what was known. So for chordal distributions, we have these bounds, and it also runs in polytime, but like as Joy asked before, like they're not tight. That I'll say beforehand. So these are our sample complexity as well as runs in polytime. So what happens in both these tree structure distribution as well as for chordal distributions, we have to somehow exploit the extra structure that this distribution gives. And without this structure, we do not know how to design polynomial time algorithm. But for both tree and chordal graphs, there are enough structures that we exploit to design poly n algorithms. So there are two things in very broad detail. So first of all, we cannot, so since we are considering the KL divergence, the probability value can go arbitrarily low, and then your error can be super high. So we have to some sort of threshold it. That's what we call clipping. And also, if we are considering the expert to be all possible distributions, I mean, that's hopeless. So we kind of bucket it to make it like a finite size. And we show that by doing these two steps, we are not losing too much error. So we can put that into our error. Okay. So for example, here, suppose this is a distribution over alphabet size 3. So this is a two. So basically, there are two free variables, 1 and 2. So like these are kind of clipped from the boundary, and this like this dots are like our experts in a sense. And the second part is, so first part is clipping and bucketing to bypass these bottlenecks, and second part is our learning algorithms for regret learning. It turns out that like this in online learning, this has been very well studied. So we'll use their known results. So they will be using two algorithms. One is known EWA, exponentially weighted average forecaster, and RWM, randomized weighted majority. So I'll see this in a new picture like in the next slide, but these are very well studied, and we'll use their regret bounds to give new learning algorithms. So in a sense, like these are two algorithms, you don't have to like go through this, but basically these are like multiplicative update algorithms. So we have all these experts, we start with their weight 1, and as the round progresses, we some sort of charge them and adjust their weights. And at every round, we are only outputting a distribution here in RWM, but in EWA, we are outputting a mixture of distribution. That's where like this non-realizable part comes in. Like the improper part comes in. Sorry. Okay. So these are our regret bounds. This is very well studied. So EWA has log-in regret, where n is like the number of experts, and this is like total regret. This is not average regret. And similarly here, RWM also has square root log. So they're good. But like as I was mentioning, like this, if we just run EWA and RWM algorithm, the number of candidate experts are so high, like we cannot do run in polynomial time. So we have to use some sort of structure on it. Okay. So how do you do this for tree structure distributions? So in a very simple sense, I'll say this. So for tree structure distributions, we first pick a single node. So suppose we have a tree structure here. So we pick the root node, and once we fix, so we can take any arbitrary node, and let's say we take this like this colored node, and then we are like, since it has only, every node can have only in degree at most 1, so we can kind of go it layer by layer, and that gives us a polynomial running time. Okay. But this doesn't generalize directly for chordal graphs. So here we use the notion of clique-free decompositions. So you have a graph this, and we'll break it into a series of cliques, and then we'll do some manipulations on this clique tree, and then this gives us a polynomial time range. So for example, let's see this algorithm. So this is our undirected graph. So suppose we fix, so final the DAG that we want is directed, like there will be no cycles. So we break it into some cliques. So this first clique that on top, so we pick a acyclic orientation of this. Now once we pick the first acyclic orientation of this clique, it some sort of fixes the direction between the nodes 2 and 3. So whatever directions that we'll give later, that has to respect the directions. So for the second part, like when we are taking the directions on this clique 2, 3, and 4, we are taking the directions of the nodes 2 and 4 and 3 and 4 such that it doesn't create a cycle. And similarly, now there are more, so there are already lots of directions. So next we will be adding those directions, those acyclic orientations that doesn't violate what we have already done. And we keep doing this, and this is finally we get this. And this is only possible because there is an efficient clique decomposition algorithm. This is not known for general arbitrary graphs. And this gives us a good sample as well as polynomial time, running time. Any questions? I'm one slide away, so I'm fine. Yeah, so in conclusion, so this is some sort of a fast learning algorithm for chordal structure distribution. Previously, like there's poly-tree distributions. Two of the authors are here, and this generalizes the approach. But interestingly, their approach and previous papers were following this natural Chow-Liu approach, which I'm not going to explain here, but if you're interested, I'd be very happy to talk about. But this is a completely different approach of learning algorithms, and it connects to seemingly different computational models. And this also gives us like some improvement in research. So for open questions, like as I already asked, like we do not know like whether our bounds are tight. So there is a huge gap. We do not know. Although like our primary goal was to get a polynomial time, so we didn't want to. But this is a very good like open question. Although, and this final thing is like in this work, we kind of connected the distribution learning with Bayesian networks. So Bayesian networks are graphical models which are directed, but there are also graphical models which are undirected, like Ising models, Markov random fields, and all. So can this be this sort of structures can be exploited to design algorithms for such cases? Thank you.
Do we have any questions for Sam? Sorry, I had one, but you just asked it yourself. So, like about the Ising models. So,
yeah. We don't know. Like it won't be direct for sure. It's not a plug and play thing because somehow we have to exploit the structures. So the issue with Ising model is that since we have to design a like a probability distribution, so there is this normalization factor which is a partition function. So like efficient computation is a bit challenging.
and you're going to be presenting a poster, but not about this.
Not about this, which will be a completely different model, which I think is interesting in its own right. So please hop by.
So let's thank the three speakers again.
Yeah. Also, thanks to like inviting me. It's been wonderful experience.
There's a special tea outside, but I have no idea what that is. So we're going to discover this. And yeah, and I think you received all